All right, well, thank you so much for that introduction, Mark. I don't think I've ever been introduced by a knight before, Sir Waltham, so that's quite an experience. But it's a real tremendous honor to be here and to be able to share some of our work with you over the next hour or so in the context of this Bakerian lecture. But as I was preparing the content of the presentation, I thought that I should learn something about the nature of this lecture series and the person who made it possible. And so Mark has already sort of introduced the notion of the lecture, the fact that a bequest of 100 pounds is what established this medal and this lecture. And so you can think about it in very simple terms, in terms of what is the equivalent purchasing power of 100 pounds back then today, and that's the $20,000 number. But I think you would have been a lot wiser if you had taken that 100 pounds and invested it in the UK stock index during that period. And if you took all the dividends and you reinvested, the compounding that happens over a 250-year period, that's a quarter of a millennium, is tremendous. And so there's a lot of uncertainty in how to make this projection, but I asked several AI agents, and I got numbers ranging between 50 and 500 million pounds. And so I suspect the Royal Society, in retrospect, would have thought that, that might have been a good idea to do that. But then I was thinking about the man himself, and I was able to pull up this biographical sketch on Henry Baker by this individual Turner, who's associated with the Museum of History of Science at Oxford. Very interested to hear and learn more about Henry Baker. And so I open up the biographical sketch. It's maybe 20 pages long. The very first page, Turner writes, "Henry Baker did not contribute to scientific research in any significant way." And I thought, wait a second, this guy is a fellow of the Royal Society. He's made this huge contribution to establish this medal and lecture. How could that be possible? And it's a sort of a harsh, kind of gratuitous way to describe it anyway. No contribution to scientific research in any significant way. And so I decided, well, I really need to read on and find out what's going on here. Page 2, Turner writes, "Baker's careful observations of crystal growth under the microscope achieved for him the honor of the Copley Medal, which is the very highest award given by the Royal Society." And it turns out he wrote many books on microscopes. He designed new microscopes. And so I have to conclude that this may be an example of some early misinformation, disinformation. So I figured I need to go back and correct it. So it really should be Henry Baker contributed to scientific research in several significant ways, not only the microscopy, but the philanthropy. And it turned out that he gave 1/3 of his entire net worth in his will to scientific societies, the Royal Society and the Bakerian Medal most prominently. And so I think the lesson here is you don't want your biography written by that guy. He's going to cause all kinds of problems for you. So then I read on. I read a lot about Henry, and then I read about the lecture itself. And Turner writes the following. He says, "Notable lecturers during the first 50 years were Tiberius Cavallo, whose 13 lectures were on a wide variety of topics." And I thought, wow, this dude knew a lot about a lot of things, And I got kind of self-conscious because I only know about one thing, and I can only give one lecture. So trying to figure out, how I can make out here. But it turns out the last 50-year period, is an equally amazing set of speakers on an incredible range of topics, but I think also just one topic each. So the system changed a little bit. But if you look at the lectures over this last 10, 15-year period, they're mostly in topics involving cosmology, fundamental physics, information theory, geology, sort of knowledge for the ages type of research and type of work in the physical sciences. Not a lot of engineering science. And so I guess I'm interested in knowledge for the ages, but in the service of technology for today. So I think this lecture will be a little bit different than maybe some of the previous lectures, and hopefully you'll find this to be interesting. And we're very interested in technology and devices. So I have a whole set of toys here that I'm going to be passing around at various points in the lecture, just to give you a sense of the nature of the technologies that we've been working on. So before I get started, I just want to thank the Royal Society again, thank Henry Baker, this famous, accomplished scientist, for his visionary bequest of 100 pounds to create this medal and lecture. So in the next 45 minutes or so, I'll tell you about some of our research in this area that's now commonly referred to as bioelectronics. So it's electronic systems designed to coexist with soft living tissues of the human body, animal models, organoids, platforms that can help us understand how biology works and ultimately how we can improve the way that we care for patients from an outcome standpoint and also from a cost effectiveness standpoint. And so I'll start with the background, give you a sense of the technology foundations, not a lot of detail here, just enough to give you a sense of what we're up to, step you through some platforms that have not only been demonstrated in our academic labs, but are now translated out into FDA and CE mark regulatory approved devices for caring for patients, not only in wealthy countries, but also in lower and middle income countries as well. I'll give you a sense of what we're doing there. And then at the end of the presentation, I'll give you some view onto sort of over-the-horizon technologies, in particular electronics that are uniquely defined by their ability to resorb naturally in the body as temporary implants, and give you a specific example of how that technology is used for temporary cardiac pacing to minimize risk to the patient following an operative procedure, a cardiac surgery during that recovery process. So my own background is in material science and engineering, but as you'll see, the work that we do is highly interdisciplinary, really blending in various aspects of physics and chemistry, electrical and computer engineering, biomedical engineering. But a lot of what we do involves deep collaborations with our medical community, and in particular, I have appointments in neurological surgery and dermatology as well. So let me give you a background, try to give you a sense of what bioelectronics is all about, and maybe it's easiest to think about that in the context of the human brain. It's biology's most sophisticated form of electronics, and ideally, if you want to understand how the brain operates or you want to modulate neural processes, you'd like to bring to bear to that problem man's most sophisticated form of electronics, the silicon integrated circuit. But there's a huge mismatch between the constituent materials, the geometries, the sort of physical properties of those two systems that create a set of opportunities for doing engineering innovation at a materials, device, and manufacturing level. So if you could integrate with the brain, you wouldn't stop there. You would think about how electronics could be used to benefit health outcomes, as integrated with other vital organs of the body. And we've done a lot in cardiac interface devices, thin, soft socks that essentially go around the outside surface of the heart to do electrophysiological mapping and electrical stimulation as an advanced form of a pacemaker. But what I'll start, to describe to you in this presentation are devices that are skin-like in their physical characteristics so that they can be laminated on the surface of the skin, exploit that skin interface for measuring underlying physiological processes that are related to health status. So that's what bioelectronics is all about. It's an effort to take that level of sophistication which exists in the form of silicon wafer-based platforms and reformulate it to look more like biology, retaining all the sophistication and function, but making it biocompatible so that it can be integrated on, around, or throughout volumetric, soft living tissues is the idea. And those devices could be temporary, they could be permanent, they could exist for only a finite period of time and then sort of disappear after the function is no longer needed. They could be static from a layout standpoint, or they could be dynamic to accommodate growth trajectories or wound healing processes. So a very rich space involving a lot of fundamental science, but thinking about technology outcomes that could really address societal challenges in human healthcare. So the question is, how do you begin to make progress, and what are the goals, and what are you trying to accomplish with that vision? And like I said before, I'll really focus on skin interface devices because we have the greatest momentum in terms of translational activities with that particular type of technology. So let me describe how we got started in this space. This is about 2008. We were tasked by DARPA, sort of the research and development arm of our Department of Defense in the U.S., with the task of developing a kind of technology that would allow for ICU-grade medical monitoring of warfighters in the field. And you'd like to be able to do that in a wireless fashion that impose minimum burden on the warfighters themselves. You would like a device that's sort of physically imperceptible, to go on the body of the warfighter and to just continuously stream data related to health status with medical grade sort of quality. And so we came up with this idea of skin-like, or what we like to refer to as epidermal electronics. And so the vision is an electronics platform that's radically different than a silicon wafer-based platform, which is rigid and planar, something that looks more like a kid's temporary tattoo. So physical properties sort of match to the skin itself. So extremely thin, lightweight, very soft and stretchable, water permeable, so you could avoid accumulation of biofluids at the interface between the devices and the skin to avoid sort of skin irritation and discomfort, but also waterproof to isolate the active electronics from the underlying soft tissues. And so the question is, how could you realize that kind of vision? And one route might involve developing entirely new classes of materials, alternatives to silicon, for example, for the semiconductor. So maybe you think about carbon nanotubes or polymer-based semiconductors, and you begin to build an entirely new electronic materials portfolio and manufacturing approach to realize that kind of vision. And we worked in that direction for some time. But what turned out to be a more productive strategy from a material standpoint is one that blends well-developed, high-performance semiconductor materials with polymeric materials in a way that realizes that vision without separating oneself from the incredibly sophisticated capabilities that are supporting the silicon electronics industry. So it's two concepts that allow you to get there. And this slide is sort of highlighting those. The first is very simple. Both are actually very simple. One is just recognizing the fact that you make any material sufficiently thin, it becomes flexible, because the bending stiffness depends, it turns out, on the cube of the thickness. So instead of a silicon wafer, which has maybe a millimeter in thickness, we like to use silicon nanomaterials, nanoribbons, nanomembranes. They're thin enough that they become mechanically floppy as a function, as a consequence of that scaling of flexural rigidity with thickness. And you can take a silicon wafer. It turns out there are ways that you can chemically etch away these extremely thin ribbons and membranes of silicon from the near surface of the wafer, still thick enough to support the kind of electronic functionality you want, but with this interesting capability to bend and flex without fracture. So you can take those ribbons, you put it on a sheet of plastic, and you can go off and you can build a high-performance, flexible silicon electronics technology. But you think about flexibility like a sheet of paper or a sheet of plastic. It's not really what you want in order to laminate onto the surface of the skin, because the skin bends, but it also stretches. And that's a fundamentally different type of mechanical characteristic that you can't achieve just by making silicon thin. So you have to add on top of that notion that thin is flexible, the idea that you can geometrically construct sort of wavy shapes in those thin ribbons, bond them to a soft rubbery substrate, and essentially what you create is an accordion bellows out of silicon. And so you can stretch this composite, this hard, soft materials composite. You can stretch it out, the amplitudes of those waves go down, the wavelengths go up in a way that avoids fracture-inducing strains in the silicon itself, but you have an end-to-end stretchability in a sense. And so with that simple set of concepts, you can do some pretty sophisticated things in sort of these hard, soft, hybrid electronic systems with soft, stretchable, skin-like characteristics. So you can exploit not only that sort of out-of-plane wavy geometry in the silicon, you can exploit not only out-of-plane but also in-plane. So you can think about structuring those ribbons into filamentary serpentine shapes. And you can do that in a 2D mesh architecture. So you have very hard, high-performance electronic materials in these filamentary serpentine mesh-type constructs, and you embed that structure in a soft elastomeric matrix. And if you pay quantitative attention to the details of the mechanics of how those soft and hard materials are interacting with one another, you can engineer this system so that it has effective stiffness almost precisely tailored to the physical properties of the skin itself, in spite of the fact that it incorporates a very hard, brittle material like silicon. So those are the ideas. That's kind of the high-level engineering approach that's turned out to work very well for us. So when you go off and you build an epidermal electronic system, you think about the materials, obviously, sort of the hard and soft hybrid material systems, almost like a deterministic composite material that you're building. You have to pay attention, like I said before, to the quantitative mechanics of how these hard and soft materials interact with one another. And then you have to overlay on top of those two considerations all the electrical engineering aspects of making a working circuit. And so it turns out that you can do all of that. And so let me describe what the end result looks like. So this is a piece of epidermal electronics. You apply it to the surface of the skin just like you would a kid's temporary tattoo. It's a dissolvable backing that provides kind of a handle so you can sort of manipulate the device. You place it on the skin, you wash away the backing, and then you have a piece of skin-like electronics intimately contacting the surface of the skin to allow sort of clinical grade medical measurements of underlying, as I said before, physiological processes that are related to health status. So that's kind of what it looks like. We published it in 2011. This wasn't a functional system, it's just a platform that had all the building blocks that you would ultimately need to build a sophisticated circuit platform. So it had transistors and diodes and resistors and inductors and antenna structures and so on. And so that's kind of what it looks like, on the surface of the skin. And of course, when you peel these things off, they're very skin-like. So they're not even stiff enough. They don't even have the mechanical rigidity to support their own weight. And so it sort of collapses on top of itself, almost like a piece of soft tissue is the way you would think about it, because the mechanical properties are quantitatively aligned to those of the skin itself. So you look at that and you might say, well, that's an interesting technology. It's kind of a wearables technology, and in a sense it is. But you think about 2011, there was no wearable technology at that time. The Fitbit Flex, which was the first wearable technology, sort of consumer-grade technology, didn't appear until 2013. From a consumer standpoint, it's a great technology. From an engineering standpoint, it's relatively primitive because it's basically just a rigid block of electronics and a battery in a soft strap that loosely couples to the wrist. So you could count steps, but without that intimate skin interface, it's very difficult to make sort of ICU-grade, medically relevant measurements of health status. So that's the approach, that's the initial device that we put together, and by now we have a whole sort of zoology of different types of devices using those same design principles, capable of mounting at any anatomical location, not constrained to the wrist or the finger as conventional wearables are. You place them wherever you need them at an anatomical location relevant to a measurement requirement or a health status. Multiple devices can be placed at different locations on the body. They can all be time synchronized wirelessly. Each device can incorporate multiple types of sensors as well. Now, like I said, that skin contact tends to be very important. If you go to the hospital, a lot of the measurements that are made require that physical contact to the skin, and this kind of epidermal sort of platform allows you to maintain that skin contact without any kind of physical perception of the presence of the device. And that's because this same kind of architecture that I described to you that provides this soft, sort of stretchable mechanics matched to the skin also has the capability to sort of conform to the complex topography that's associated with human skin. And this is a colorized SEM just showing sort of that geometric conformality and the ability to sort of follow the contours of the skin. That provides a very low impedance measurement interface. So using the skin as a window to measure underlying physiological processes. So those are the ideas. It turns out you can load these kinds of epidermal electronic platforms up with all different kinds of sensors. And so we and a large independent collection of researchers who are active in this space have developed a broad portfolio, broad toolkit of sensor types that are compatible with this epidermal electronics platform. So all kinds of precision thermal measurements, electrocardiograms. You can measure brain waves, hydration state. You can even embed tiny fluid channels into these devices so you can capture very tiny amounts of eccrine sweat as it naturally comes off the surface of the skin. It turns out to be a rich source of biochemical markers of health status to complement sort of biophysical measurements. You can measure different kinds of mechanical characteristics, strain, motion, modulus, pressure, optical measurements as well. You can embed light-emitting diodes, photodetectors into the same platform. You can measure body sounds. As I mentioned before, each device can include multiple different types of sensors, so they're multimodal. You can mount many different sensors at different locations, wirelessly time synchronized, like I mentioned before, so it's multinodal as well. Where there's a clinical predicate, you can aim for clinical quality. In many cases, you can realize that level of quality, but you don't have to constrain yourself to just clinical measurements that are made today. You can think about de novo measurement capabilities, and I think looking at sweat biomarkers is a good example of that. The wireless operation allows you to capture data continuously in a hospital or a home setting, and so you can move away from an approach to health management that relies on episodic evaluations of health status when you show up to a hospital to one that's driven by large data streams continuously collected during normal daily life. Now, it turns out that cost turns out to be very important sort of metric to think about. And we really view cost as an engineering performance metric that you innovate and you optimize around, because we want to develop technologies that are not only available to wealthy countries, but can be used even in resource-constrained areas of the globe, lower and middle-income countries, so the technology is available to everyone. And I'll come back to that topic in a few slides. So now you have the technology. What is the most compelling use case? And so we talked to our medical collaborators, various people associated with the hospital system in the Chicagoland area, and we decided pretty early on that the most urgent need for this kind of wireless skin-like clinical grade monitoring technology was in the neonatal intensive care unit. So these are premature babies that require 24/7 monitoring of all vital signs continuously. They're in a very fragile health status, but they're currently monitored by technologies that were originally developed for adults. And they're highly inappropriate for these tiny premature babies. They involve tapes that can damage the fragile skin of the babies, hard biosensors fixed to the surface of the skin with those tapes, hardwired connections to expensive boxes of external data acquisition electronics, and it creates all kinds of problems, not only injuries to the skin, because you have to apply these sensors and remove them typically on a 12 or 24-hour cycle so you can execute routine clinical operations, diaper changes, that kind of thing. The wires actually constrain the natural motions of the babies, and what we didn't realize when we got involved in this effort, it became clear once we were recruiting patients for our pilot studies, is that the parents were very interested in making the wires go away so they could more frequently and more intimately engage with their newborn. And so the idea and the vision was to replace the rat's nest of wires, replace the expensive data acquisition electronics, replace the invasive tapes with 2 or 3 of these wireless skin-like devices to capture all of the same kinds of vital signs, but without all of the disadvantages associated with the traditional systems that exist today. So I'll just fast forward. I've described the basic engineering principles around these technologies. It turns out you can engineer a pair of these epidermal electronic platforms to reproduce all the vital signs that are being monitored, even at a very sophisticated NICU facility like the ones that we have at Lurie Children's Hospital in Chicago, other places here in the UK as well. 2 devices, one goes on the chest, and it's monitoring cardiac activity. So it's capturing electrocardiograms, and it's doing that wirelessly and in a battery-free fashion as well. And the initial studies involve not only the clinical standard with a wired-based system, but our devices as well. And so we can do a one-to-one comparison of the accuracy, the precision of the measurements. It turns out it's actually better than the wired-based systems because you eliminate a lot of noise associated with motion of the wires. Because it's intrinsically a wireless system. So that's the device that goes on the chest. From those electrocardiograms, you can get heart rate variability, respiration rate. There's a precision temperature sensor in that device as well. You're getting the surface temperature of the chest, but it can be calibrated fairly well to core body temperature. But that's not all. You really have to measure blood oxygenation as well. And you do that with an optical technique. So again, it's this epidermal platform, but now it's operating based on light illumination from extremely tiny light-emitting diodes at 2 colors, illuminating the underlying skin. And then there's a photodetector that's measuring the backscattered light at those 2 wavelengths. And with that kind of measurement, you can determine blood oxygenation. You also get a redundant measurement of heart rate variability, and respiration rate as well. So that's what it looks like on a premature baby coming through Lurie Children's Hospital. The hand there on the right is Aaron Hamvas. He's head of the Department of Neonatology at Lurie Children's. You can see our device here. These are the wired-based systems, and this baby is being monitored in an active operating NICU facility. So we have to develop the hardware, but you want the neonatal nurses to use these devices. You also have to develop a graphical user interface that replicates what they're used to looking at with their Philips or Draeger monitoring systems. So we were able to do that, put together the software, the hardware, and really enter this device into routine patient care at Lurie Children's, all the way down to 26-week deliveries. So 24 weeks is commonly known as the edge of viability. So that's about as young a baby as you will ever see in a NICU facility. And so these devices apply all the way down to those youngest patients. So I have a couple of these devices. I'll pass them around. They're single use, so they're in boxes, and you can't sort of pull them out and flex them around because they are somewhat fragile. But I'll pass these around, and you can sort of check them out. I need these back at the end of the presentation, so these are not free samples. My students would kill me if I didn't get them back. So that's what it looks like in the NICU. Those are the technologies. We were very successful in the NICU, so we migrated out into the PICU associated with Prentice Women's Hospital, also in the Chicagoland area, so larger babies, but still benefiting from a wireless solution. And here's an example of a baby coming through the PICU. You can see the device on the chest. That's capturing that cardiopulmonary activity. The device on the foot is capturing blood oxygenation. So these are operating in a wireless fashion, obviously, but they're also wirelessly powered. So we use an RFID tag type antenna, which is mounted in the base of the chair or the base of the isolette. It's able to wirelessly deliver power to these devices to support their operation. It also provides a wireless link for capturing real-time data streams from each of them. And they're also time synchronized, so you get hemodynamic information. So you can measure when a cardiac cycle occurs to launch a pulse of blood passing through the arterial system, and when that pulse of blood arrives over here, we know exactly what the time delay is. And so that time delay can be correlated to blood pressure. So it's a pretty good non-invasive way to sort of track changes in blood pressure by measuring that pulse wave velocity using time synchronization. And that goes beyond what's done even in a sophisticated level 4 NICU facility. And so making the wires go away, there's just tremendous benefit to that across all of pediatrics. This is a pretty interesting picture because it shows you the kind of mechanics, the skin-like mechanics of these devices. You see the device mounted on the back. In this case, the baby is engaged in what's called kangaroo mother care, so it's chest-to-chest contact. That skin-to-skin contact has a very strong therapeutic benefit to the development of the baby. And in this case, it's a little bit easier to get wireless signal out of a device that's mounted on the back rather than the chest. As you can see, as the baby turns around to look at the cameraman here, the skin kind of wrinkles in a natural way, and the device just follows those wrinkles without perturbing them. So that's this whole skin-like notion associated with the device engineering. So in order to make this happen, I had mentioned this at the outset, but it's very interdisciplinary. So it's material science, mechanical engineering, electrical engineering, biomedical engineering, computer science, but also intimately engaged with the clinical community. So we can understand what the challenges are, what the devices need to look like. So the head of dermatology, head of neonatology, head of pediatrics, all co-authors on this original paper published in the spring of 2019. But what we found out is that the nurses, in many cases, provided the best sort of practical input into what's going to work, what's not going to work, how we need to modify things. And so there are several nurses who were co-authors on this paper as well. So that was spring of 2019. This captured a lot of interest in the popular press. I got a phone call about that time from program managers at the Gates Foundation and the Save the Children organization. They were aware of the work, and they were very interested in asking us and finding out whether we could adapt that technology for economically viable deployment into lower and middle income countries, resource-constrained areas of the globe where cost becomes an overriding important consideration. And so what they told us is, number one, it could not be single use. Everything that's done in Lurie Children's, most modern hospitals, all the monitoring systems, all the sensors are single use, and that's what we designed to. But you can't make that work from an economic standpoint. The cost goes through the roof. So you have to have devices that can be reused hundreds of cycles so you can amortize out of the cost of patient care the cost of the device itself. So number one, it had to be reusable. Number two, it could not rely on this RFID tag wireless power transfer because there's no reliable source of wall plug power in many of these countries, so it needed to have battery power embedded in the device. And the third requirement is that the devices had to be compatible with smartphone technology, so the smartphone itself could be used as the monitor, so you don't have a separate cost associated with the monitor. So they provided funding for us to go off and do that and to run the cost models to verify that we could hit the cost targets that need to be satisfied for this particular use case. So about a year later, we were able to re-engineer the devices with those considerations prioritized, and we were able to do that. And so I'll pass around a couple of those devices so you can take a look at them. They're much more robust, so you can play around with them and throw them around if you want. More like Band-Aids now than skin-like electronics, but still sufficiently soft and flexible to apply to very young infants. And so these are the data streams that come off of the devices that are being passed around now. So we're doing ECG. Photoplasmography gives you blood oxygenation. That's the next two data traces you see there. But we're actually going beyond standard of care because we have a high bandwidth accelerometer. So it's actually measuring cardiac sounds. And so it's like it's a continuous streaming stethoscope signal coming off of the devices. That's not done today. But you get complementary information from cardiac sounds compared to what you see in an electrocardiogram. So anyway, tremendous amount of data, tremendous amount of high quality data that you can extract various sorts of health insights from. Typically, the physicians only want to see heart rate, SpO2, respiration rate, and temperature, and that's very easy to do. But I think there's a lot more information embedded in that data and a huge opportunity for AI algorithms to extract some of those insights, and that's something we're working on currently. So we're able to hit the metrics. We're able to work then with the Gates Foundation, and as I mentioned before, the Save Children organization, not only to do the engineering work, but actually to deploy using their boots on the ground into these various challenging areas across the globe. So this is the first deployment, a training session. A couple of my students up in the front of the room. This is in Zambia. So these are health workers being trained in how to use these devices. Now, the value of monitoring in these places in the world is that there's a constraint on the number of healthcare workers that are available. And so there are more babies than can be monitored, easily. And so you'd like to be able to triage that limited resource to the babies that are in greatest need. And so that's kind of the value proposition here. Now, there's a lot of mortality associated with premature births in these parts of the world. There's also a lot of mortality just associated with childbirth itself, so maternal mortality. And so this worked out pretty well. So the Gates Foundation came back and said, could you develop a suite of sensors that will allow us to monitor maternal and fetal health during the intrapartum period, during the entire birth process, to sort of pick up signs of complications that may affect health outcomes for the newborn and also the new mother. So it turns out we could do that. We take those two sensors we were using to monitor the babies, modify them so that we could monitor the expecting mothers, and then we add a third device, time synchronized with the other two, to measure fetal heart rate and uterine contractions. So now you have a complete suite of devices that replicate the kind of monitoring capabilities that are used in hospitals during a birth process. So I won't go through the details. Again, we validated the technology to gold standards and showed that these platforms can offer equivalent or better data quality than what is available with traditional wired-based systems. And so we're able to scale these and deploy these at a more aggressive level. Almost 500 pregnant women in Zambia presenting, and we're mounting them with these sensors throughout that intrapartum period and tracking all the health parameters during the birth. And so this provides a hint into where things are going. So this is not quite population scale, but you have 500 data sets. You can begin to think about not only determining the instantaneous health status of a pregnant woman and her fetus, but maybe make predictive assessments of what is the likely health trajectory. Is a C-section going to be needed? When is the birth likely to happen? Are there likely to be complications to further improve the way that we provide care? And so that turned out to be a very exciting proposition, again, for the Gates Foundation, but in this case also for the Steele Foundation for Hope, another philanthropic group that got involved in some of this work. This time through a startup company that we had to launch to allow us to scale at levels of deployment that are difficult to support just with PhD students and postdocs. And so this was the first deployment of the maternal fetal systems last year, January. We were in Rwanda, Kenya, and Nigeria. And so I'm here. I'm just watching. It's actually the Cybele Health guys are doing all the work here. But it was very exciting to see this technology and the kind of impact that it can have in these resource-constrained areas of the globe. And so the Gates Foundation has been a great partner for us over the last few years. I think we are one of the most prominent programs within the entire Gates Foundation portfolio. This is the front cover of their annual report for just this last year. And these are technologies out of our lab. There's the device monitoring health of the pregnant woman. That's a staff engineer at Cybele Health, and there's a graphical user interface there. So we're very excited about this. It's an engineering-oriented company built around technical excellence and trying to address challenges in global health as well as healthcare in wealthier parts of the world. And so they have multiple clearances, an entire portfolio of devices. I'm wearing a couple of them right now, and so if you're interested, you can find me after this presentation. I'll give you a sense of what the data looks like, what the devices are all about. I don't know, stripped down here, but you can see right there. Anyway, I got 2 or 3 of these things on me right now. So anyway, measuring my stress level, I guess, is a little bit what's going on. But almost 10,000 systems, 20,000 patients, 20 countries. We have a great partnership with Draeger, which is a German company that has a strong presence in medical device, especially in Europe. And so it's very exciting. We teamed with Draeger, and we were part of an open competition for wireless health monitoring in the hospital system associated with Denmark, the country of Denmark. We won that. And I think we won it because the nurses were so intrigued by the soft, flexible mechanics of our devices. And by comparison to the competition, these rigid pucks just wasn't nearly as exciting. And so we're deploying into Denmark. We have patients mounted up in a couple of hospitals in the Copenhagen region. We're also here in the UK. So NHS Lothian, there's a GI patient. We're tracking surgical recovery. So that's a hospital in Edinburgh. Another example of a deployment into into this part of the world. So that's all the kind of work that's going on at the Cybele Health team. It's about 130 people, mostly engineers. We have a medical doctor as CEO, so very exciting. I think it's on a very productive track, and if this all works out, I think it'll really have a qualitative impact on the way we care for patients, both from an outcome and a cost standpoint as well. So what are we doing in the lab then? We're playing around with new form factors, new geometries, working closely with neonatologists to understand how to even better care for these patients by exploiting the design versatility associated with these concepts I shared with you at the beginning of the presentation. So here's one example. I'll pass this one around. So it's more like a strip of electronics anatomically matched to the sort of the side of the baby. It turns out that that's sort of an ideal mounting location from the standpoint of wireless communication, connectivity, and it also allows us to separate the 2 electrodes for measuring electrocardiograms to a much greater degree than we otherwise would be able to do. And we're also measuring impedance as a way to track respiratory cycles. So that's with Montreal Children's Hospital. I'll pass that around. Take a look at that. And we're deployed into their NICU as well. So what else? Here's another advance that we're working on, just to give you a sense that this is evolving area of technology, lots of opportunities, is thinking about how small we could make these devices. We make them so small that we could just like sprinkle them around on the baby at anatomical locations of relevance. And so this is unpublished work. These are button-sized electronic systems that offer clinical-grade wireless measurements of health status, all different kinds of measurements, electrocardiograms, motion, SpO2, photoplethysmography, temperature, sounds, brain waves. And so I'll pass around one of these devices. It's in this container. Keep it in there. You can probably drop it and lose it. But anyway, a little button. This is designed to go on the forehead to measure cerebral oximetry and electroencephalogram, so brain waves, just give you an idea. So you can really mix and match depending on the health status of the baby and use as many or as few of these as are necessary. So let me give you one final example of a future direction, something that we're working on at the research level, and this is in the realm of what we refer to as filamentary electronics. And so there's a famous fetoscopic surgeon associated with Lurie Children's Hospital, Amin Shaban. He was aware of our work in wireless sensors for monitoring the health status of premature babies in the NICU at Lurie Children's Hospital. And he called me up and he asked whether I could adapt those kinds of technologies for monitoring the vital signs associated with a fetus during a fetal surgery. And I had no idea about this. I had no idea this was actually even happening. But there are surgical procedures nowadays that are performed on a fetus prior to birth. And the idea is that the intrauterine space is an ideal environment for healing. And so you'd like to do the measurement before birth so that the infant can heal but before it's born. And this is typically done with congenital defects such as spina bifida, as illustrated here. So the idea is you come in with small hollow metal ports that come through the abdomen to allow for insertion of surgical tools to perform the operation. Up to this point, though, the operation is performed sort of in a blind, open-loop fashion because you don't have any tracking of the vital signs of the patient in this case. That'd be very unusual. You go into an invasive operating room for a surgery like this on an adult, you would have full vital signs monitoring the patient at all times. And so that was the challenge, is how do we do full vital signs monitoring on a fetus during a fetoscopic surgery? And so we really had to change the geometry entirely, because the only access port is through those surgical ports. So you have to have a device that's small enough and thin enough to fit through those tiny metal tubes so that it can be positioned and interfaced with the fetus to allow full vital signs monitoring. And I won't go through the details of this. A lot of the same design principles and the same material science, but really collapse down to a hair-like filament that can be inserted directly for monitoring of the fetal health continuously during the operation. So we have not used this on human fetuses yet, but we have done large animal model studies. And so these are pregnant sheep. This is a massive undertaking, multiple surgeons. It's like a full OR suite. They do operation on the fetal lamb, and in this case, we're monitoring, the health. And these filaments actually, we put very tiny balloons along their length, so we can pneumatically activate these balloons. And so the probe actually goes down the esophagus. It's a great place for doing vital signs monitoring. And you inflate the balloons to ensure good contact between the sensors on that filamentary probe and the soft tissue in that lumen. And so you can capture all vital signs in that way. So with that, I'm going to shift gears. I have like 10 minutes left and talk to you about something a little bit different. So a lot of the ideas in skin-like electronics, these filamentary probes and so on, can be used for implantable technologies, not just devices that sit on the surface of the skin, but devices that go inside the body. I talked about brain interface electronics and cardiac interface electronics at the very beginning of this presentation. We can do all of that. You think about the use cases for an implant of this type. One would be as a chronic implant, maybe a replacement for a traditional pacemaker in the context of those cardiac interfaced soft electronic platforms, or as a advanced surgical diagnostic or surgical tool where the residence time on the soft tissue would be measured on a time frame comparable to the operation itself, maybe a few hours. For the permanent implant, you're thinking about a few decades, maybe life of the patient. And so those are two use cases that we're pretty much aware of. What we didn't realize when we got started in this space is that there's a whole set of opportunities that lie in between those limiting cases where you might need an implant, not permanently, not just for a few hours, but maybe for a few weeks, to monitor an internal wound healing process, or monitor a patient and deliver therapy, for example, during a post-surgical recovery process. And in those scenarios, you would like the device to go in, offer high-performance, stable operating capabilities during the clinically relevant time frame, but ultimately you would like the device to just melt away and disappear after it's no longer needed, so that you would thereby eliminate any risk associated with an unnecessary device load on the patient without going in and doing a secondary surgical extraction process. So it's conceptually like a resorbable suture, but instead of just providing a dumb mechanical function, it's full electronic capabilities. And so that brings me back to this slide. So this idea of bioelectronics, so biocompatible electronics that's temporary. And what could you do with that, and how would you even begin to build a class of electronics that could just melt away harmlessly in biofluids inside the body? And so that brings me to this notion of bioresorbable electronics. Again, very similar to a resorbable suture, but now with full electronic functionality, wireless communication capability, light emitting, detecting, whatever you can think of. Those capabilities would be available to you in this kind of technology. So how do you begin to do it? And for a while, we thought maybe it's going to be impossible. You don't think about electronic materials as being water soluble, because for the most part, they're not. But what turned out to be the case is that these super thin silicon ribbons and membranes that we were interested in for their mechanical properties, this bendability and ultimately the stretchability, it turns out that it revealed an ultra-slow chemistry that nobody really knew about, which is that silicon itself is water soluble. It just dissolves at an incredibly low rate. So you would never see that dissolution happening at a wafer scale. It's too thick. It's a big bulk piece of material. You drop it into a bucket of water, you're not going to see anything happen. But if you're playing around with these silicon nanomembranes, that very slow rate of dissolution becomes qualitatively important in the way you think about the material. So now you have a silicon nanomembrane, and a very attentive postdoc was actually able to observe this. You immerse it in water, saline solution at physiological temperature, physiological pH. Over the course of a few weeks, it will dissolve away completely. But it's dissolving at a super slow rate, like I mentioned before, a few nanometers of erosion per day. So just a few atomic layers per day is how slow this is happening. But the silicon's gone completely, and furthermore, the reaction is silicon reacts with water to form a compound known as silicic acid, which is already naturally occurring in groundwater. It's biocompatible. Actually, silicon is a recommended part of a daily diet, and a little bit of hydrogen. And it undergoes surface erosion in a very controlled way. So you can measure, let's say, the height or the thickness of one of those nanomembranes, and you can just track it linearly decreasing with time, measured in days. So you start out with a nanomembrane with a thickness of 100 nanometers. It's totally gone in 3 weeks. And so that was very exciting. It was a serendipitous discovery. We happened to be playing around with these nanoscale forms of silicon, and we noticed, hey, silicon is water soluble. That was a very exciting moment, because this semiconductor material is typically the most challenging material for any class of electronics. And now you have access to silicon for a water soluble class of electronics. Now you can begin to make progress, because there's a whole set of metals that are water soluble, good conductors, but also water soluble and biocompatible: magnesium, zinc, tungsten, molybdenum, iron. All of these minerals are essential for natural metabolic processes. You can also pattern them into electrodes and conducting wires and so on. You put it all together, you can build a piece of electronics that's uniquely defined by its ability to dissolve away in water. And this is a simple RF oscillator showing how you can put all those materials together to begin to build functional, high-performance classes of electronics. Here's an example. It's just sort of a movie to show dissolution of that kind of electronics. It's magnesium for the conductors, magnesium oxide for the dielectric, ultra-thin silicon for the semiconductor. It's a MOSFET and an RF diode, and silk fibrin, so it's a biomaterial that we're using as a substrate, and the encapsulation layer. So now you can build water-soluble, biocompatible electronics. What do you do with it? And so it turns out there are a lot of things that you can do with it. Let me just describe one of them, and I'll pass around a couple of devices to give you a sense of what this is all about. So there are a couple of cardiac surgeons associated with our medical school that were aware of our ability to build these resorbable implants. And they called me up and they said, can you build a wirelessly powered, wirelessly controlled temporary pacemaker that we could use with our patients? I said, what's a temporary pacemaker all about? So it turns out that if you come into the hospital and you have a structural failure or a valve failure in your heart, in many cases that will require very invasive surgery. So you're opening up the chest or you're doing a catheter-based surgery. Very invasive. The patients themselves are typically not in a terribly healthy status coming in. Now you have this very invasive procedure. What they like to do then in many cases is they leave a temporary pacing lead in the body of the patient, interface to the heart, passing transcutaneously out to an external power supply so that they can pace the heart if they need to during that recovery period. If the heart rate drops below a threshold level, they can pace it back up to a healthy level as an emergency precaution. But ultimately the patients get better. That temporary pacing lead is no longer needed, so it has to be pulled out. And while it's there, it's physically tethering the patient to an external power supply. So a few disadvantages. And their vision was if you had a resorbable pacemaker, you could implant it completely. You wouldn't have the transcutaneous lead. You wouldn't need the external power supply. You could fire it up and pace the heart as necessary. But ultimately, the device would just dissolve away after it's no longer needed. You wouldn't have to do the surgical extraction. So you might say, well, it's just a pacing lead. Why can't I just pull that out? What's the big deal? Maybe there's some risk there, maybe to the skin or something. It turns out that the pacing lead, when it's in contact with the cardiac tissue during this recovery period, it's typically 3 to 4 weeks, it will be encapsulated in fibrous tissue, scar tissue. So that when you pull the lead out, you tear the scar tissue, but in some cases, tearing the scar tissue leads to tearing of the healthy cardiac tissue, in which case you create an internal bleed that can lead to patient death. And so this is the challenge that they were aiming to overcome by working with us on a bioresorbable alternative to this kind of temporary pacing. Furthermore, it turns out that this kind of temporary cardiac pacing is commonly used for pediatric patients who have to undergo a cardiac surgery. So not only do you want something that's resorbable, wirelessly powered, wirelessly controlled, but as small as possible also, because we're talking about tiny babies, and the hearts are very small. So just to give you a sense that this is a risk, and kind of as a point of reference, it turns out that Neil Armstrong passed away due to complications associated with removal of his temporary pacemaker following a cardiac bypass surgery. So they pulled it out, it caused an internal bleed, the physicians didn't realize that was happening, his blood pressure dropped catastrophically, and he passed away as a result. So let me just fast forward. This is the device that we put together to address that need. It also happens to be the world's smallest pacemaker. It's also bioresorbable. So I'm going to pass that around. It's in this little vial. It looks like a little ant, but it's actually a pacemaker. And I'll describe how that works. So it consists of two parts, and it's all bioresorbable, by the way. So it's two parts. It's a pair of electrodes, both out of metals that are bioresorbable, but they're dissimilar metals. So they form a galvanic pair. When in contact with biofluids, it's basically like a primary battery. So it's a battery driven by bioresorbable metal electrodes that also establish the electrical interface to the cardiac tissue. Okay, so that's the battery. How do I operate it then? The other side of the device consists of a photoactivated switch. I won't get into the details of this, but when you illuminate this device with near-infrared light, that switch closes and the battery can then discharge current into the cardiac tissue. If I'm not illuminating the device, that switch is open and the battery cannot discharge current into the cardiac tissue. And so near-infrared light has a very deep penetration depth into soft living tissue. And so what we do then is thinking about post-surgical recovery monitoring. Now we're doing monitoring, but we're also doing therapy. So I mentioned the case of post-surgical monitoring in the context of NHS Lothian. Here's an extension of that. So it's two parts. It's the implantable, bioresorbable millimeter scale pacemaker that's delivering the therapy as needed. And then we have a soft electronic patch that goes on the surface of the chest. It's doing two things. It's measuring electrocardiograms, so we measure heart rate. It has a computational facility in here, so it can compare that measured heart rate to a physician set threshold. If that heart rate drops below the threshold, then it automatically activates near-infrared LEDs on this side of the device in a pulsatile mode, pulsing that cardiac pacemaker at a rate that increases the heart rate back into a normal, healthy level. So it's operating in a completely closed-loop fashion in a wireless modality. So I'll pass this around as well, so you take a look at the LEDs and the electrodes for measurement and stimulation. And so these are demonstrations on a large animal model. I'll leave you with two more things, sort of advanced versions of this. So these are little light-activated wireless stimulators, essentially. So if you put a filter on these devices, then they're wavelength selective. So you use different color LEDs to activate different pacemakers depending on what kind of color filter. So you can do multi-site pacing, which allows a higher level of sophistication and control of cardiac rhythm. So you can do biventricular pacing, and the timing is set by how you activate the external LEDs with these different colors. So you can do biventricular, you can do atrial and ventricular pacing, lots of different things. And now you can think about optical wavelength division multiplexing of lots of these devices, and you think about them not only as a cardiac pacemaker, but you can sprinkle them on the brain, on the spinal cord, on the peripheral nerves, the vagus nerve, all sorts of applications that we're looking at. And you can control them independently using different wavelength LEDs, as I mentioned before. And so this is the final slide, and this is the notion of using these tiny electrical stimulators as a way to enhance the functionality of otherwise conventional implants. This is a heart valve framework that is delivered in a transaortic catheter-based approach to address valve failure in heart patients. And we can now use these stimulators to do the same kind of cardiac pacing following that kind of surgery by just mounting them on that frame, which already exists and is already, FDA approved for use with humans. So I apologize. That's maybe a lot of content, but I think I'll just wrap it up there and highlight a couple of the platforms that I've shared with you, over the last hour or so. These epidermal electronic devices. Origins in an academic research lab, but now deployed at a global scale, LMICs, Denmark, UK, Canada, the US, and other places for patient monitoring. And then sort of a next generation type platform that we're still working on sort of at a research level, but these, these ideas in bioresorbable electronics and these very tiny electrical stimulators and cardiac pacemakers. So with that, I'm just going to conclude by acknowledging senior collaborators. We're a very collaborative group across not only engineering science, but very critically across various areas of clinical medicine and medical science. List of the senior collaborators associated with the work that I shared with you. But I also want to acknowledge the team at Cybele Health. So all those deployments are done by the Cybele Health team. I'm not involved at all. All credit to them. Very exciting they're able to get to that kind of scale. But most important for me anyway are the students and the postdocs who actually do the work. I just get to talk about it. So we have an incredible team, undergraduates, master's students, medical students, PhDs, postdocs, some senior staff members as well. Funding agencies, I mentioned the Gates Foundation, Steel Foundation for Hope, DARPA, Kimberly Query and Lou Simpson also provide a very important philanthropy to enable this work. And I'd also like to thank my spouse, Lisa Dar, for putting up with me and crazy work hours and providing all kinds of great advice over the years. But maybe most importantly, I want to thank the Royal Society for enabling me to share this research with you this evening. Thank you very much.
Thank you very much indeed. That was absolutely astonishing and really clearly delivered. I'm sure there'll be lots of questions. So in the audience, hold your hand up. This may or may not work, but we'll see. I suppose to kick off, the demand for these devices must be enormous because, the whole diversity of uses. How do you actually manage with all the people that want to try them out?
So I have a pretty big team, so we have probably 30, 40 projects going on at any given time. A lot of them, probably 2/3 to 3/4 of them have origins associated with inbound requests for technology from the clinical community, so we're not trying to sell our technology. It's not kind of set up in that way. It's funny because I get kind of three categories of inputs from the clinical community. One is for a technology that you could probably hack together in your garage, not really suitable for PhD research. The other is kind of in the realm of Star Trek, where you have to, break laws of physics in order to make it happen. So you're looking for that sweet spot, something that's intellectually challenging, maybe aligned with our unique capabilities. And then you think about like the patient impact, and you try to prioritize both on both of those considerations. Yeah.
And how difficult are they to manufacture? Are there many companies that potentially can do this or not?
So Cybele Health has used an outsourced manufacturing partner. So some of the device manufacturing assembly is happening outsourced, and then they do the final assembly and encapsulation and quality control. So that was another consideration in terms of hitting the cost targets that the Gates Foundation, Save the Children organization put in front of us. We needed to develop a technology that could leverage existing manufacturing capacity to keep the costs as low as possible. So it was another sort of engineering optimization that we had to think about, is alignment with sort of bleeding edge capabilities and flexible printed circuit board technology.
And how do the regulators keep up with you? Or how do you keep up with the regulation?
Well, I don't want to get into all the details of CE mark and how difficult that process is. That's a 24-month process. We have, I think, 17 FDA clearances, various conditions, various patient populations. So it's possible. It's pretty straightforward if your device has a clinical predicate. So you only have to show equivalency. to accuracy and reliability. So if your device kind of falls into that category, it's typically for the US FDA, it's maybe a 12 to 18 month process. It's 1,000 pages of paperwork. It's not any walk in the park, but kind of doable. CE mark for us has been closer to 24, 25 months. Just a little bit slower.
Who'd like to ask questions from the audience? You're all sitting there. There we are. Very good. There should be a microphone coming. Where are the microphones?
Thank you for the fantastic talk. I have two questions. What's the best way to put the research into practical work and the industrial area?
That's a pretty open-ended question, I would say. I mean, it's a great question. It's hard to answer that in sort of a generic sense. I mean, I think maybe my introductory remarks, I tried to convey this notion. I mean, we're interested in fundamental science, but we want to do scientific discovery in the context of answers that lead to practical technologies. So we think about practical aspects at the front end of our research efforts. I mean, some of it's just open field, lunatic fringe research. I think you need to do a little bit of that as a university group. But we've done product development in the past, and so I have a good kind of intuitive sense of what's going to work in terms of scale and manufacturing and reliability and robustness in operation. And so I kind of place my filter on some of the ideas that bubble out of the group, and we try to kind of use that experience, I guess, and intuition in terms of making an assessment of what's going to be successful in terms of translation out of an academic laboratory environment. But other than that, I think it's hard to give kind of a sweeping, broad answer to that question, which is a great question, but it would need to be framed in the context of like a specific technology and kind of describe that. But maybe in the context of what I shared in this presentation, I think that epidermal electronics, that was something that we were striving to do as almost like an engineering challenge. Like, how thin can we make it? How skin-like in terms of the physical properties could we engineer those systems? And it was successful at that level. As I mentioned before, it's just single use, but everything that's in NICU today is single use, so there's really no problem with that, except for uses in these resource-constrained areas, these LMICs. But it turns out that it was probably a little over-engineered, because when we came back to the same collaborators in NICUs at Lurie Children's and Princess Women's and Montreal Children's Hospital with these thicker kind of Band-Aid-like devices, they're fine with that. It's still much better than the wired-based system. So we may have kind of over-engineered things a little bit, with those skin-like devices. And from a practical translational standpoint, it's much more challenging. It's just much more difficult to build those devices. It's finer interconnect wiring. It's thinner. They're more fragile. And so the cost structure and the manufacturing challenges are much more significant than they are associated with those more soft kind of Band-Aid-like devices. So in some sense, the Gates Foundation and the Save the Children Foundation kind of nudged us in the right direction, for making these things commercializable at scale, not only for LMICs. The interesting thing is the exact same devices going into Zambia are going into Denmark, going into NHS Lothian. It's exactly the same technology. And so, I think cost is important for everyone. It's maybe a higher level of importance, when you're really resource constrained. The other thing that turned out to be interesting is from a sustainability standpoint, it's much better to have devices that can be reused hundreds of cycles. You eliminate a lot of the solid waste associated with the single-use devices. So that's been a key selling point, I guess, for Cybele Health, is it's wirelessly rechargeable and reusable. Spec'd out to like 1,000 cycles or something like that. So, yeah.
Good question there. Hands now going up. So, one each side there, and then one.
I have a second question.
No, sorry. One question.
Fascinating work. It sounds like sci-fi, but without the fiction part, and that brings me to think. So the problems you're solving are far more important than neonatal care and cardiovascular problems. Have you considered, mostly on the research basis, have you considered using these sensors in space exploration?
Oh, yeah. No, that's a pretty clear area of opportunity. It doesn't sort of pack the same punch in terms of impact. you know, vulnerable populations, pregnant women, fetuses, neonates, you know, astronauts, you know. Maybe Neil Armstrong, you know, could have used it. Yeah, I think it's a great area of opportunity, but a little bit lower down our priority list. I would say I have my priorities in terms of, you know, what we work on, but realistically, it's the student enthusiasm and the passion that sort of drives where the research goes in terms of the overall operation. Babies, women, elderly people, yeah, people get very energized about that, yeah.
Okay, there's a question this side, and then can the other microphone go to the back, please? There's a question right at the back. And then I think that's going to have to be it, unfortunately, although I think there are a million questions to ask.
Thank you very much for the talk. So my question is about the bioelectronics on the brain. What's the application? Is that for measurement or for the stimulation?
Yeah, great question. So we got involved in that particular area through a collaborator, neurosurgeon, Professor Brian Litt at University of Pennsylvania. So he reached out. So this is back before we were actually doing biointegrated electronics. We started working on large area flexible displays, military systems, lightweight, deployable, high-speed antennas, communication systems for the military. And he approached us asking whether we could take that flexible electronics, put it on a brain. And his interest was in classes of surgeries that are used to treat severe forms of epilepsy, which involves taking the skull cap off, placing an array of electrodes on the brain to identify which region of the brain is responsible for the seizure. So you put the mapping electrodes on the brain, wait for a seizure to happen, and then you can determine from the spatiotemporal pattern of electrical activity which part of the brain needs to be resected. So he was doing those kinds of resection surgeries, but the spatial resolution was not that great with the kind of, they're called ECOG arrays that are used today. So he was interested in active electronics that would allow you to do that kind of spatiotemporal mapping at a much higher spatial and temporal resolution, so you could more accurately define the region of the brain that needed to be resected. So you would resect the minimum amount of brain tissue. So that's how we got started. So it was a surgical diagnostic is the way you could think about it. It would be on the brain for a few hours, a few days at most. Yeah.
Excellent. Mm-hmm. Last question.
Hello. Thank you for the talk. I have a question on biological grounding, or like the importance of comparing the measurements of your device to some ground truth. Do you find that that's something your clients really want, a very precise measurement, or is it something like, okay, better than what we have now, adopt?
Great question. So for FDA approval, as I mentioned before, if there's a clinical predicate, so there's a wired-based system for measuring ECGs, you have to show that your technology is at least as good as that. Could be better, but at least as good. It has to be comparable to that predicate device in order to get regulatory clearance for using the device on patients and using the data from your device to guide clinical decision making. You can be better, but you have to be at least as good. But there are other devices I didn't talk about today that offer de novo measurement capabilities. So there's no clinical predicate. And there, the FDA regulatory process is much more complicated, and it requires a long discussion with the FDA to define the kinds of experiments you need to do and the clinical studies that you need to perform to show that the device is operating as advertised. So it's a different pathways, de novo, or it's 510K or de novo. It's predicate or no predicate. Yeah.